Okay.
Okay, so we can start?
Yeah, we can start. Can you hear me all right?
We can start. It's
Yes.
rolling.
So, good afternoon, everybody, and welcome to the our last meeting in this webinar series, Environmental Sustainability and International Cooperation. It has been a pleasure to develop this path together in these months, and we now have our last webinar on a topic that was not really discussed too much in the previous editions, and it's about geohazards and natural hazards. And today we have a guest speaker for this seminar, who is Professor Balaji Hariharan. I hope, Balaji, I said your name correctly. Sorry for some mistake.
Yeah, Balaji. It's okay.
Balaji.
Yeah.
Okay, yeah. Thank you. And Professor Balaji is a professor at the Wireless Network and Application Center at Amrita University in India, in the southwest of India, in the state of Kerala. And we are partners. Amrita University and the University of Trento are partners since several years through some formal memorandum of understanding, bilateral agreements, and mobility programs. And we had the pleasure 2 years ago to develop a piece of work together with a group of students from Amrita, a group of students from Trento, from environmental engineering, working together in the field in a mountain area where the wireless network, the Center for Wireless Network and Application at Amrita University has a pilot study site, especially in relation to hydrogeological risk and landslides. And I think we will learn a bit more about this context in the talk of today, because our colleagues have a long-term monitoring program in this site and in this area. And if I can add just a few more words, we found a converging interest in addressing environmental issues, especially issues related to, in this case, hydrogeological risk, by combining the technical part, the technical studies on triggering factors and dynamics of landslides and also floods, together with the participation and the involvement of the local communities. And so integrating in some way the technical studies with the social studies. Just before starting, as we did also in the last editions, in the last webinars of our ESIC series, we have prepared a very quick instant poll for all participants to answer. So you'll find in the chat the link to access the poll. And before starting the webinar, we ask everybody to go to this link. You will see 3 questions. Just give your response, your answer to the questions. We'll leave just a couple of minutes and then we can start the webinar. If any of us, of the guys, of the organizing team has the view of how many answers we have, just give me a sign. So when we are close to completion, we can start. Are we close to the completion of the poll?
Yes, we are.
Okay. And last word, in the program, you have seen that the talk was supposed to be given by Professor Maneesha Ramesh, who is the director of the Center for Wireless Networks and Applications. She could not made properly the connection because of travel obligation today. And so the talk will be given by Professor Balaji, and whom we thank a lot for his availability. And I'll just give him the floor for the talk. Thank you, Balaji.
Thank you very much, Professor. So my name is Balaji Hariharan. I am from the Amrita Center for Wireless Networks and Applications in Amrita Vishwavidyapitham, which is a huge university here in India. So today I'm going to talk about a little bit about the university, about our center, and more information on the work that we are doing here. Okay. So like the slide shares, this is the name of the university, Amrita Vishwavidyapitham. We are currently ranked number 4 in India in the ranking, National Institutional Ranking Framework done by the Government of India. And this is including all, Indian Institute of Technology and all the other institutes which have been around for a long time. So we are a fairly young university, and we have grown really fast, and we have grown really well, I would say. So that is what has caused us to be in the 4th rank now in India. We are a private university, and basically this is our chancellor. She's Amma. And she basically drives the university's vision and mission. And she is a very, very well-known humanitarian. World over, she is well-known as a hugging saint in some places. The whole vision and mission for the university is education for life and compassion-driven research. So these are the two key indicators that drive everything that happens here. Our center, Amrita Center for Wireless Networks and Applications, basically it's a very, very interdisciplinary center. We have a lot of people. We have engineers, we have mathematicians, we have physicists, we have geoscience people, we have electrical, electronic, mechanical engineers, all kinds of disciplines. And nowadays we have even doctors and people from the medical area in working part-time in our department. And the reason that we are very interdisciplinary is because these are the main aims of our group. Basically to develop solutions to solve challenging societal problems. So everything that we do in our university as a whole, but in our department specifically, is driven towards providing solutions to the society. And we used state-of-the-art technology, and we collaborate with a lot of people around the world. So we have a fair amount of research going on, and also we have education arm. So we have people, we have a postgraduate program and doctoral program in the department. So we have a lot of masters and PhD students who also participate in that research, and also that way the research is also getting disseminated. So in our center, we offer multiple master's programs, and we work on various different research themes. Our focus today will be on this IoT for extreme environments, which is the kind of topic that I'm going to address today. Okay, so under this umbrella, basically we have done several projects. By far the biggest one is the landslide early warning system using intelligent IoT sensors that we have developed. We also have other projects going on in flood monitoring. We have projects going on in offshore communication systems for fishermen, and we have landslide multi-hazard risk reduction. So the first and the last is kind of tied together, and I will tell you as we go along. Okay. Okay. So today's topic is basically going to be real-world experiences, IoT system for landslide early warning in India. And of course, this is supposed to be done by Dr. Maneesha Ramesh, who's the director of our center. Unfortunately, she's stuck on the road somewhere with not very good network connectivity. So I'm doing this for her. What is landslide? Yeah, does anybody have any question, or do we reserve questions for the last?
I think we can reserve the questions for the last.
Okay. So what are landslides? Landslides are defined as a movement of rock, debris, or earth down a slope under the influence of gravity. If you are from the geo background, you know all about it, probably more than I personally do. My background is a computer scientist. I've been working on this particular project for nearly 10 years, or a little over 10 years now, actually. Landslide is one of the worst affected. India is one of the worst affected countries due to landslide, because we have over 12% of the land is prone to landslide, and they contribute about 18% of the global casualties among all the natural hazard related calamities in India. So it's a big thing in India. So if you look at the type of landslides, there are different classifications for landslides. So the landslides can be falls, they can be topple, they can be slides, they can be spreads, they can be flows, and the variability, the variability in terms of triggering parameters, initiation threshold, runoff area, spatial impact, meaning how much space is getting affected. So if you lay it out on a table, it kind of looks like this. This is the table, actually a reference that I picked up from USGS landslide handbook. Basically, the key triggers for landslides can be intense rainfall, prolonged precipitation, supersaturation, subsurface, vibrations due to seismic activities like earthquakes, flooding, snow melt, rapid drawdown, volcanic eruption, or human-induced triggers like hill slope modification, blockage of drainage path, especially of small streams and rivers that happens to be there in the area, induction of artificial vibration due to mining and related activities. So if you look at all the triggers, they fall into some major categories. So they can be meteorological, they can be geological, they can be hydrological, and they can be natural, or they can be man-made. And the triggers vary spatio-temporally. So what we mean by that is depending on the area and the space, it can vary, and depending on the time, temporally also, it can vary. So for monitoring landslides, what are the key requirements? So if you split them into multiple categories, on the spatial side, you can have a single event. Event meaning a hill a few kilometers in a region, and you could have a landslide being monitored in that region. Or you could have a multi-hazard scenario where we can think about it as a catchment scale. That means 5 kilometers to up to 100 kilometers. We can give some level of monitoring we can do in the spatial range. Again, on the temporal side, we can do rainfall-induced landslide, which is predominant in the monsoon period. So what do we mean by temporal is the landslide may not be triggered by the rainfall in this particular instance when the landslide happened. There could be anticipatory events. That means, there is a continuous heavy rainfall over the last 1 week or 1 month, and that is causing the landslide that is happening at this moment. So there is a temporal variation. So that means basically what we are saying is, when we study landslide, when we want to manifest landslide, we cannot depend on instantaneous data alone. We have to look for temporally distributed data as well. And then if you look at earthquake-induced landslides, there's uncertainty in the event generation. And also the data can be historic, can be real-time. You can look at historical data, and we'll also talk about a little bit about how we use historic data in some of the algorithms that we use. We can do forecasting. Forecasting can come from you personally, like us in Amrita, or from the meteorological department from the government. They can do rainfall forecast. We can use those data as input to our model. So we can do things like that. Communication, what kind of communication do you want? I mean, we are talking about communication technologies here. How do we communicate? How do we collect the data? How do we communicate? And then we also talk about dissemination of the data and the triggers that happen, and how our model is predicting, and then how do we disseminate those alerts to the people who are affected. So that also involves community engagement. There's basically multi-stakeholder engagement, and some of the events can also be recurring events. So for example, here, especially in India, where we have monsoon has just started in India. So monsoon triggers a lot of landslides. So it can be an annual occurrence, and exactly where it's going to happen is not known. But then using our models, we are able to do a fairly good job of predicting what is going to happen. So if you look at the temporal monitoring data, so weather variability, weather can be, we can look at rainfall at an hourly rate, at a 1 day daily rate, at the last 7 weekly or monthly rate, and forecast. We can look at the forecast from the meteorological department. So how the weather varies. What are the triggers? The triggers can again be instantaneous triggers. Something like a seismic event will be instantaneous, but something else like a poor pressure buildup will be, going on over a period of time. And then context. What is the context that is driving this? So this again can be, the data can be measured in terms of milliseconds or days, or it can be historic months and years. We have to use all these kinds of temporally varying data and feed it into our model. Okay, and then causal relations, multi-thresholds. There could be multiple factors that are affecting, are playing into this landslide event. So we have to study those clearly. There can be dynamic decisions that are being made, and the decisions can again be, temporally distributed. It can be, in terms of seconds or hourly or daily. And, when we talk about historic months, years, and forecasting can also be done in hours and days and so on. So when we talk about multi-scale warning, which is what our model is about, again, that can be, on a temporal basis, it's very vastly distributed. Okay. When we talk about spatial monitoring of landslides, so we have these various categories. Obviously, we'll be deploying our equipment and our instruments in some area that is called the site. And then where the entire slope, the site is located, that will be the next spatial area that we can monitor. There could be a catchment area, which is similar to what I talked about earlier, 5 to 20 kilometers, 25 kilometers away from the site. It could be regional, it could be global. So how do we have different levels of monitoring on the spatial side? So if you put all these together in a table, so basically we have site level, slope level, catchment level, regional level, global level. What are some of the techniques that are used? Slide and slope, obviously you need to have physical sensors which are located at the site. That's why it's called a site. A catchment can be based on, physical sensor, drone-based remote sensing, crowdsourced data, things like that. Regional can be satellite-based remote sensing. Global can be satellite-based. Regional can also be crowdsourced data. And how often do we collect the data? So if you look at the data frequency, as you go up from site to global, the data frequency kind of decreases, right? So in site, we can have a high frequency, sub-minute or even minute-wise data collection. As we go towards the catchment, it becomes less frequent. As we go towards the global, it becomes even more less frequent. And then we have developed models, different kinds of models, which can be applied to each of these different scenarios. And what are some of the thresholds that can be developed? Again, for site, we can have very location-specific sensor-based thresholds. For catchment, it can be an integration of multiple different thresholds. For regional, again, integration of catchments. Global, it's something even higher scale. So basically, how is the decision being made? So it can be a single scale decision, multi-scale, and so on. And then warning, the area that is being covered and the site, obviously, it's only the site. That means a specific location within a slope. A slope is like a hill, a slope of a hill. Catchment is, like I told you, several kilometers from the area. And then regional can be a state or a district or whatever. It can go even up to national, and then global is even bigger. Now, when we talk about reliability of the model, obviously, because we have physical sensors and equipment placed on the site, the reliability is going to be very high. But as we move towards the global, the reliability is going to decrease. So what are some of the challenges? In spatial versus temporal, basically, when we design a system, this is what we have learned over 10 years of our experience. This is what we have learned. You have to make compromises. So you can go for highly spatial, accuracy, highly temporal accuracy, or somewhere in between. So usually, it depends on the deployment, the scale of the deployment, the number of people who are getting affected, or who are in the what do you call alerting area. So based on all that, the cost, of course, is a big factor. Based on all this, you have to do a compromise. So you have to do whether we go highly spatial or highly temporal, or what ratio, what level in between. So that means you have to think about what area you're going to monitor. Is it going to be a large area, or is it going to be just a slope or just a side? Are you going to use location-based monitoring, or are you going to use multi-parameter monitoring? And again, reliability and cost. Like I told you in the previous table, as you go from a site specific to a global, the reliability is going to increase, but the scale is going to become larger. So we have to put a compromise between reliability and cost, large-scale deployment or high frequency. What is the frequency of data connection? What is the sensor system that we are going to use? Are we going to use homogeneous or heterogeneous sensors? What is the cost, and how much can we simulate this? Or how much can be done in the laboratory and the model can be done? So some other factors that we can consider is heterogeneous versus resource constraints. So are we going to do multi-domain based monitoring? What are the constraints in terms of energy? Are you going to deploy in a very what do you call developed place, so there is no constraints on energy? Usually what has happened, at least in our experience, it is usually deployed in very remote areas, but there is a population around that area which is getting affected, and so we have to deploy. It's a question of lives that we are going to save. So there is constraints in terms of energy that is available, in terms of what power, what level of powerful systems can be deployed there, what kind of communications technologies can be deployed, can we do local processing? So these are some of the constraints we can think of. On the geospatial side, we have to think about whether we want to do heterogeneous data. That means multiple different types of data being collected, rainfall, pore pressure, movement sensors, things like that. And then how do we do dynamic thresholds in that scenario? Local decisions versus global decisions. So this again affects what kind of coverage you can get, what kind of connectivity is available. For example, if you are going to deploy in an area where it's very difficult to have a network in place to transmit the data outside the region. So it's a very remote area, so there's no networking available. So you might have to do a large amount of decisions locally. So these are some of the constraints, challenges that we have to face in landslide monitoring. And again, these are some of the geospatial monitoring enhancements that we can do. Heterogeneous sensing techniques can be used, resource-aware service management, learning temporal interrelationship, spatial interrelationship, dynamic decision models, multi-scale warning. So all these are done. And these are done by using different methods, different techniques. It can be remote sensing based, can be physical sensor based, participatory sensing, where we involve the entire local community to do that, energy efficient, context aware, real-time, delay tolerant, fault tolerant kind of networking communication. And then we used a lot of algorithms, especially nowadays with machine learning and artificial intelligence. We have really used a lot of that ML and AI concept here to drive some of these enhancements in our geospatial monitoring. Okay, so all these has resulted in we came up with a system which is considered the world's first system for monitoring rainfall-induced landslide using sensors, wireless sensor networks specifically. So it's an IoT-based wireless sensor network system for detection and early warning of landslides. Detection can be done fairly simply, but early warning is the difficult part. And then how do we do this? So basically in this, we do sensing deep earth layers, which basically helps us in predicting the data using some AI and ML integrated models and thresholds, and then site-specific to regional, how we can transform. We can basically use our site-specific model and enhance it to give you a regional prediction forecast. Okay, so all this we've developed through what is called an IoT-enabled deep earth probe. It's called a DEP for short, deep earth probe. So basically, this is a probe that goes as deep as maybe 25 meters into the earth, and it carries all kinds of sensors inside for geotechnical and other measurements. And then at the top of the probe, Earth probe, you have an intelligent wireless node, which is basically acting as an edge node in our entire architecture. We have deployed this in Kerala, which is in South India, in a very, very landslide prone area. You can see actually a landslide happened here. Are you able to see my cursor? I hope so.
Yeah, yes, we can.
Yeah, so the landslide has happened here in the slough, and there's a huge community here. So they are under real and present danger whenever there is rainfall in this area. So our system is deployed somewhere here in this region, and it's really helping them out a lot. So we got several awards for this deployment. It's one of the biggest ones we have got is for what is called the NABARD award, done by the Government of India for Rural Innovations. And then the number of lives that have impacted in 1,000, 5,000 plus. We have also secured a fair amount of funding. Now, this was our first deployment done in 2006, and then which is about 15 years ago. And then this is actually the principal scientific advisor to the Government of India, the top scientist in the country. He was very, very impressed by our work there. So he made us deploy another system in the Himalayas, in Northeast Himalaya. I'll also talk about that. So our system was able to issue warnings, early warnings in 2009, 11, 13, 18, 19, and 20, several years. And we also, I'll also tell you how the warnings have become increasingly more accurate because of the way that our system has been enhanced over the period of time. Okay, so this is a deployment in Western Ghats, and this is the deployment in Himalayas, in Sikkim, landslide prone areas. I don't know how clear this picture is, but we've tried to compress everything in a slide here. So this is our deep earth probe that I talked about. All kinds of different heterogeneous sensor, moisture sensor, geophone, tilt meter, pore pressure sensor, strain gauge, rain gauge. All these are part of this deep earth probe and intelligent wireless node that we have here. And basically our system works like this. So we have a field network, and then from the field network, we have a gateway through which all the data is gathered. And then through the network, through multiple means, we have fault tolerant network. So we have traditional networking like a DSL line or something if it's available in that area. We're able to carry the data through that. We also have a satellite backup. Now with the latest advancements, we have used LoRa and all those other type of communication for sending the data. So the data goes to the data management center, which is located on site. From there, it is further sent to our data management center, which is here in our university. This is where the models are developed, the alerts are issued from here. There's a fair amount of processing that goes on in the data management center, which acts as an edge node to do some amount of local decisions, and the global decisions are made here. And then, like I said, we've tried to compress everything into one slide. It is deployed here in Kerala and here in Sikkim, which is in the Himalayas. And we also have a visualization system, which is put here. Especially this is taken when a warning was issued. The yellow indicates the fact of safety crossing. And so the threshold crossed and the warnings are issued. So milestones, the first deployment happened in 2006 which started as a FP6 program called WinSoc. We had 11 European partners which started this entire program. And then we actually finished the deployment in 2008. The first warning was issued in 2009. The government took notice, and the highest level parliament, they appreciated the work we have done. Warnings were issued, patents, we filed for US patents were granted. And then we took in a lot of international partners, and then we have collaborative international projects starting in 2017. We were awarded a World Center of Excellence for this work by the International Program of Landslides, IPL, in 2017. It was for 2017 to 2020 for 3 years, and then it got renewed again from 21 to 23 now. So we are continuing to be the World Center of Excellence for awarded by the IPL program. In 2018, we had the second bigger deployment in Sikkim and Himalayas. We have done a fair amount of work. So if you look at the IoT, I'm getting into the nitty-gritty details of our system now. So it will get a little more technical at this point. If you look at the IoT system in our landslide early warning system, it's a multiple feature integrated system, multi-layered system. These are all some of the features of the system. Dynamic learning is there, AI being used for dynamic learning, dynamic decision model, integrated warning, automatic system. So all this, it's somewhat similar in functionality to the USGS seismic system that they have, that any earthquake happens anywhere in the world, there's a system that is automatically triggered and issues an alert. Similar to that we do. And then the alert is vetted by the experts in the system, and then it is further communicated to the government and the local population. So I'll talk about the multi-level warning. But the first level reaching the researchers is all automatic. There's too many things here. Maybe I won't go into all the nitty-gritty details, but basically we use a combination of edge network, fog network, and cloud computing in our system. And basically we've split it into multiple layers. So there's a sensing layer which collects all the data. It could be heterogeneous sensors, it could be homogeneous, or it could be just a single sensor. With a rainfall sensor, we could do some amount of prediction. If cost is the prime concern, or all you can afford is a rainfall sensor, then we can use that also. So our system kind of scales really well depending on the deployment scenario. Data acquisition system, from the sensing, the data is acquired, and then the acquired data, some amount of logic is used, global decision making, data aggregation happens, and then the communication layer. It basically we use different mechanisms here: wireless, wired, heterogeneous, mix. Excuse me. Communication layer, and then the network layer. Network layer does clustering and localization algorithm, time synchronization, which is a big issue, especially when the scale of network is somewhat high, which is what we have. It happened to us in our Sikkim deployment. That deployment covered an area of 43 hectares. So it was a huge area spanning multiple hills. So we had to really work on this time synchronization algorithms to get everything going. And then the knowledge absorption, what kind of spatio-temporal variation are there, things like that. And then the data goes into cloud analytics and forecasting, multi-level dynamic threshold development, slope stability modeling, fault diagnosis, and so on. And then how do you disseminate what we have done? So risk alerts, how do we do risk alerts, server cloud level network of fault. So because we have multiple levels, we also have multiple levels of failures possible. So that means we need to have properly fault tolerant at each of these levels. So you could have sensing layers failing, data acquisition failing, communication network, any of these layers or a combination could be failing. So our system has to be designed in a very fault tolerant way in order to get over failures in this very complicated system. So if you look at heterogeneous
Balaji, I just joined. I just wanted to add a point in the previous slide.
Yeah.
Now this is Maneesha from Amrita University.
I'm glad you could join, Maneesha.
Hi, Maneesha, welcome.
Hi.
Thanks
Hi,
for
everybody.
joining.
Finally, I could reach.
That's great.
Yeah, I just wanted to add one point here. Like when you think of geohazards, this framework is bringing in how you can integrate monitoring, detection, and forecasting from a slope to site to catchment scale to regional scale monitoring of geohazards. So when you have edge, fog, and cloud, the area of their monitoring varies in this scenario. In the edge, it will be more localized, whereas in the fog, it is collecting from different edges so that it becomes more of region specific data will be coming on the fog layer. And what is majorly what we need to take care of here is the need of heterogeneity. The domain itself demands heterogeneous knowledge and heterogeneous parameters to be monitored. So that need to be integrated at multiple levels of each of the layers. So this demands the interoperability, and because of that, we have to have interoperable platforms which can work together so that it will give us scalability to connect multiple fields of heterogeneous characteristics to give us a global view of variance in the disaster itself. So that is why such an IoT framework is necessary for monitoring geohazards. Balaji, you could go ahead.
Do you want to continue? Are you having a good connection? It's up to you.
I think you can continue wherever I am needed. I can jump in. I reached back.
Okay. Okay, so if you look at the IoT edge computing and analytics, like I told you, this is a deep earth probe. It goes all the way sometimes up to 25-30 meters under the surface, and it usually covers multiple layers on the slope. So and depending on the layers that it's going to monitor, we put the necessary geosensors. For example, depending on the water table, we can choose to have a moisture sensor at different levels. If there is movement, then we can put the necessary sensors to monitor the movement and so on, strain gauges and geophones. So basically, it's our solution allows us to vary the kind of sensors that we put, but our framework supports everything together. So that is what Maneesha was saying in the previous slide also, that our framework has to be able to support the different scenarios because each site is different. Each natural hazard that we want to monitor is different, but our system has to support everything together. And then if you look at the edge nodes and services, so we have, this is kind of a software stack that is shown here. So we have, different types of hardware, analog and digital type of hardware that is being used in the picture. And then we have a device driver layer, which is able to talk to all of them. And then we have the framework contains sensor management module, network management module, and other, this is basically database and other services which are running here. So this is basically our software also has to be designed in order to be able to support this. Maneesha, you want to add anything else?
This is where each of your knowledge in the geohazards will come in designing the IoT edge layer itself. When you say heterogeneous sensing, it varies, the sensors will vary with respect to the characteristics of the geological and hydrological characteristic of that particular field. Based on the subsurface layers and its properties, you will decide which type of sensing parameter you need. If you have really a layer which is very vulnerable, which is very capable to actually to hold on the water and increase the pore pressure, you will need a pore pressure sensor to measure it. Whereas if you need a layer which is very vulnerable and it is going to slip And that is the layer in and around. You will need the movement sensors, the vibration sensors. So based on each location, what is the type of sensors and how many sensors and what the arrangements will change. Based on that, your service requirements will also change. That's why you will need a sensor management, and you will also need the power or the time synchronization management will come in. So you, and also since these edge nodes has to be living long time, we have to come up with effective algorithms which will manage with respect to context. Balaji, maybe you can go to the next slide. So that is where Amrita has designed a context-aware energy management system where it uses the domain knowledge from landslide to understand which are the sensors to be activated at what temporal period. So you may need for the moment monsoon initiates, you may need the rainfall sensor, but you may not need the pore pressure from that time itself, because it will take time for the pore pressure to build up. So you can keep it switched off, and at some point when the pore pressure is about to start building, you can switch on. So dynamically, you have to learn this at what point each of the sensor has to be switched on. And using that dynamic prioritization, you activate the sensors so that it consumes less amount of energy and you will get the more lifetime for the whole sensor node. So if you see the graph on the right hand side, it shows you that the context aware energy management algorithm takes where will have more remaining power compared to the other ones. And based on that, only that much data you need to send, so that you are also saving the bandwidth required for wireless transmission. Balaji, maybe the next slide. All this data which is coming in adaptively with respect to context is sent through the heterogeneous wireless network. So you have three networks. You can see there is a probe network, there is a field LAN, and there is an adaptive one. So the probe network is specifically with respect to a site or a slope specific, where you have multiple IoT edge nodes collecting different data parameters, sending it into the regional locations where it will do the first level analysis and then send to the cloud or to your control station wherever it is far away, which is the adaptive one. So when you have in the adaptive one, it is basically connecting different fields together. So it does a much more complex scenario like a cloud server. And in all these connections, one of the major thing is you will need to have multiple wireless or wired type of connections to make sure fault tolerance is taken. So we have built a 24/7 operational landslide monitoring and detection and delivering real-time warnings by integrating sensors, the wireless networks, and software. Balaji, the next slide. And all this data which come to the central location are we are able to visualize using a web portal, which is our real-time data visualization from world around, from anywhere. You can see the data from multiple fields, from the multiple sensors, and also the decision models are integrated into this visualization so that you are able to take the necessary action also based on this data. All this software has been in-house built at Amrita University. Can we go to the next slide? So what is the crux? The crux is it is not enough to get the data. You have to actually move on from data to information to the knowledge discovery. So what we have done is over the years, we have collected a lot of data, and based on those data, the decade long, we have collected the data, and that data has gone through real-time data analysis and then the adaptive learning and forecasting. So next slide, please. And these decision models basically look into the meteorological, the geological, hydrological, and the vibrational models. So it brings in the spatio-temporal analysis through data mining models, and also it brings in machine learning models for threshold models for heterogeneous sensor networks. Move on to the next slide, please. So one of the examples which we have used the rain gauges and the landslide susceptibility map and the landslide events in the area of Sikkim. With this map shows you the study area of Sikkim, which is in the northeastern Himalayas, and in the right side down corner you can see the map which is showing all rain gauges and the landslide locations, and the susceptibility map onto its left. So all these are combined together. Next slide. and we have built the regional thresholds and local thresholds. So in the regional rainfall thresholds, we were able to propose our own rainfall threshold equation, which is equal to I is equal to 43.26 d raised to minus 0.78. So if you see that, the equation indicates that there is lesser chance of landslide occurrence in Sikkim if the rainfall is below 43.26 millimeter in a day. And for a rainfall event of 30 days duration, the minimum intensity comes down to 3.04 millimeter per day. Can you go to the next slide? Whereas in the case of the site-specific rainfall threshold, according to the equation, it is I is equal to 100 d raised to minus 0.92, and it talks about is the slope instability would not occur if the rainfall received in the day is less than 100 millimeter. So it clearly shows the variation, and we were able to actually work with the previous data of more than 10 years and also the real-time data which we have got from for the last 4-5 years. Can you go to the next slide? So we validated the whole models with our real-time data which we have got from 2015 to 18, and we have looked into the true positive cases, true negative case, false positive, false negative, etc. And the proposed threshold was able to correctly predict true positives, 9 out of 10 available landslide events. And during the validation period, only a single missed alarm was identified. Could we go to the next slide, please? So, but what we have learned is it is not enough to just give me a second, just one urgent call is coming, 1 second. So during the what we have learned over the years is single parameter cannot predict things in the best fashion we need. So we have started looking into the multiple parameters like rainfall and pore water pressure data. And what we had seen is the antecedent conditions have much bigger impact on pore water pressure, and cumulative rainfall was showing an impact in it. So we have actually analyzed over the years. Can you go to the next slide? So here, if you see, the blue line shows the rainfall events and the yellow line shows the pore pressure events. And if you see that for a long period, if you take the year 2013, for a long period when the rainfall happens, the pore pressure remains at a lower level of about very closer to maybe 2 kilopascal, etc. But then suddenly you have a very high peak rise. You can see that. This means that if you don't carefully plan your data collection and transmission, you may miss the event. So you have to very carefully work closely with the domain knowledge to have this capture correctly, so that you don't miss the event which is coming just later that. So that is one of the major important thing. And you can see that the impact of one parameter is seen in a delayed fashion, because it will take time for it to actually percolate down these water, infiltrate, and then generate changes in other parameters. Could you go to the next slide? So using this knowledge, what we have done is we try to find out what is the interrelationship, and we have tried to use different machine learning algorithms, including neural networking, decision models, support vector regression, etc. And what we had seen is in the support vector regression, we had got much better results, and we have used historic data and build a model for support vector machine in regression, and also an adaptive model which uses historic data and also the real-time data. And if you see the blue color is the actual pore water pressure line, and the red color is the output from the model of support vector adapt, and it almost follows the same thing. Using this model, we are able to give a 24-hour ahead of knowledge about the landslide, imminent landslides, because from the pore water pressure, we are able to talk about the factor of safety, and that is used for giving this 24-hour ahead information about imminent landslides. Could you go to the next slide? So it's and not only that, we also had other parameters which I have deployed. This is from the site in the northeastern side of Sikkim, where we have deployed movement sensors. In one of the particular location, we were able to see that for a period of 18 months, the system measured a cumulative surface displacement of 0.146 meter, and an average rate of surface displacement throughout the whole period of monitoring was 8.11 into 10 raised to minus 3 meter per month, with peak rate in range of 0.03 meter per month during the monsoon. Could you go to the next slide? So in the next slide, you will be able to see a vertical profile of the same location. If you see that the signals from this intelligent wireless probes in the middle region of the hill indicate that the existence of slip surface is at a depth of 14 meters. And within a 6-month period from 2019, 7th month to 2020 January, you can see that the slip surface activity has been diffused to a depth of 16 meters, indicating that the shear band associated with the slip surface is becoming wider. This clearly demonstrates that it is highly necessary for these vulnerable locations to be continuously monitored and analyzed to understand how the risk is increasing. So there is a rainfall increase, which is telling you how the slip surface movement is happening. When you integrate it with purpose, it is giving you much better idea of how it is happening. Now you integrate with movement, it is giving you a more reliable results where it is happening and what location it is happening. Could you move to the next slide, sir? This gives you the data with respect to microseismic data, which we have collected from the same location. Could you go to the next slide? So you can see several peaks here. So what it has done is there was actually a slide which was a small sliding which happened in 19 June. And this data clearly shows that the signals were detected in the middle region and also in the cloud region. And the vibration signals were captured even pre-event and also the post-event. Both sides we were able to capture the respective signal patterns and the respective spectrums for the 3 axes of geophone. Could you go to the next slide? And what we had seen is because we have deployed multiple types of sensors, we could see that 10 hertz geophone was able to take the dominant spectral peaks in these small movements. And so we are further doing a lot of enhancements and trying to understand much better on what are the type of micro movement, what are the micro seismic vibrations you are getting, etc. Could you go to the next slide? So we are not constraining us only with the sensor system. To understand better about the landslide phenomena and the slopes instability and how each of these parameters are influencing, we have developed a medium scale laboratory setup and large scale laboratory setup, where these laboratory setups are built with automatic simulation of rainfall. With different rates, you can simulate as the same water droplet size, and you have seepage simulators, and it has the capability also to simulate multiple soil layers so that it can give us the different soil layer interaction. So we vary the different conditions and we try to understand how the phenomena will happen, what is the time at which you will expect an event to happen if the particular parameters are kept at some level. So from the field also we learn the parameters, we give it to the landslide lab and we see where the threshold we are expecting. Some things which we don't see regularly at the field, we will still do at the laboratory and then give back to the field. So it helps us to actually build the knowledge in the landslide domain and use that for bringing in the thresholds, bringing in the data collection frequency for each of the sensor systems. Could you go to the next slide?
Yeah, I would just like to add one more thing, that this lab is a big driver for our modeling that we do for our landslide forecasting, because here we actually make the landslide happen with the exact same soil that we collect from the sea and the kind of sensor that we would deploy in the field, and we study what is actually triggering the landslide to happen. And this is a big input that we provide to our model. Go ahead, Maneesha. Sorry about that.
And using all these things, we have proposed a multi-level warning system. So it has 4 levels of warning. The first level warning, which uses only global rainfall thresholds. And when we see that that warning is initiated, the system automatically informs the researchers. In the second level warning, it actually uses the site-specific, a combination of site-specific rainfall thresholds, moisture thresholds, and pore pressure thresholds, which will initiate the second level warning, which will come to researchers and government. In the third level, it will actually take not only these things, along with that, the dynamically learned stability parameters also. And if it shows that there is a chance of movement, it will also inform researchers, government, and to the media. Which based on the government instruction. And in the fourth level, it will also take the real-time data from the movement and the vibrational thresholds and the factor of safety slope stability models, pore pressure threshold, site-specific, and also the dynamically learned multi-parameters, which will help us to release it to public based on the national disaster management policies, because normally warnings has to be issued by the disaster management. So we give the information to the government, take the permission, and then percolate it to also automatically through SMS, emails, and calls to the local population, our populace also. And it's not just along with the sensor data, we also take along with the field data, we look into how the landslide laboratory setup will give us the answer for the same condition, what is the slope stability models are giving. All of these things are validated before the warning is gone. Next slide, please. So this has been extensively used, and in 2018, when the Kerala floods happened, it was like a multi-hazard scenario where you had extreme rainfall of 42% departure from normal and flood of 14% of total land area of Kerala, landslides 200 plus. And because of this heavy flooding, they had to open the dam. 36 dams had to be opened at the same time, which even led to change in river course. So all districts of Kerala, the state of Kerala became red alert, and the death toll became 450 plus, and displaced more than million people has been displaced in the over that period. Could you go to the next slide? And during this period, this shows how it was impacted, and it was a major impact. And this type of scenario Kerala experienced once in 100 years. So it was very unprecedented scenario. Could you go to the next slide, please? And what we had seen is our system was able to showcase its societal impact by delivering the effective landslide early warning during this time. And our decision model has issued 3 effective warnings, one on 12th July, another one on 15th July, and 9th August. And the landslide happened on the 11th of August, I think. And because of our warning, they were able to evacuate and move the people to the safer places, and life was saved. And this is how our visualization will show how the ranges of alert are changing based on the alert levels and different sensors. The colors will vary, and it will automatically also inform through email, SMS, etc. Could you go to the next slide? So what I want to more or less tell is, like, can you go to the previous slide once more, Balaji? Why I say it enhanced the reliability of early warning, because we were able to give a regional warning saying that within this area, within the 10-kilometer purview, you are going to have landslides. But we were also able to confidently tell that in the site, in the slope which we have deployed, landslides won't happen. So the people in our area, there was no need to evacuate, and they were not evacuated. Only the other people have been evacuated, and the landslide happened not on our side, on the nearby sites. So it showed the reliability, and because of that, people are believing in the warning which Amrita is giving. And we were able to even give landslide early warning issued in 2020. These are the emails which go to the Kerala State Disaster Management about the landslide, the imminent landslides, and these are the regional warnings. Could you go to the next slide? And here on August 6, 2020 in Munnar, Western Ghats, we had given a regional landslide warning for Munnar area. On August 7th, the devastating landslide happened in Pettimudai, Rajamalai, which is 20 kilometers away from our deployment site in Munnar. And in this area, what is happening is you have multiple TA states, and you have more, and this area almost more than 80 people have died because of landslides. So what is happening is this is more of regional, but you are not able to localize there because your instrumentation is in a site specific area. You're able to say that in that site is not going to happen. But you're at the same time, you're able to say in this region, all the vulnerable locations, your vulnerability or the risk is increasing, and please be aware that there is going to be landslides. So it also brings in the point that in each of these areas, if we can go a little more deeper and come up with the multi-parameter based monitoring, you will be able to pinpoint, localize, and say where the landslide is going to happen, and that way you can save the life. Could you go? And which shows that the validity of the IoT system.
Yeah, and also the machine learning and AI model. I think that is a big driver in this whole thing that she's talking about multi-hazard scenario, because the interplay between the different factors, something like AI and machine learning can really help you in that area. Yeah, go ahead.
These are the different, different thresholds which we used for the daily, the hourly. I think we can skip these slides, Balaji. Next slide and the next slide. So we never limited as our work with only the IoT. We have a large work with respect to the flood side also. We have an Indo-German project called Flood Evac, where we work with TU Munich, University of Mannheim, etc. Several of the German universities were part of this whole initiatives with us, and where what we were looking into it, we are using the computer vision and image processing methodologies to understand how the flood level is increasing, and based on that, in real time, you inform them which path is getting more flooded, which path they can use, etc. So in that process, we also have built a crowdsourced mobile application, and which is called Amrita Kripa app, which is really available at this point of time in the Google Play Store in Android. And this has been used effectively, which is the output from that project, has been used effectively during the Kerala floods in 2018, and we're able to say provide relief and rescue to more than 120,000 people who were affected by this floods. And it basically looks into a crowdsource. It is a crowdsource application. A lot of volunteers, a lot of victims, a lot of state governments and volunteers were using it, and it was providing an opportunity to connect the dots and making sure where in each location where people are stuck, how we will go there, what is the mode of ways you can send the people to rescue, like, because the flood became so much, you don't know where the road is, you don't know which is the landmark, no landmark you can find, all those things. You have to send boat, you have to send helicopter. So all these activities we were able to do. Along with that, our students at the university has started a 24-hour call send-up. You can see the students sitting there. They were sleeplessly working for weeks to do this whole effort and coordinating with all of the different agencies by utilizing this mobile application to save the people. And it is a geo-referenced application which help us to do everything like food, medicine, all the relief materials, and at the same time even rescuing each and every person from the flood wherever we could get the information.
Yeah, I would just like to add that this app and this call center together, we were able to coordinate with the local disaster management people, with the state disaster manager people. And at some point, like Maneesha was saying, it became so huge, the Navy had to be called in. And the Navy people also were coordinating with us. They were calling our call center to find out who needs help where. They were using our app to figure out everything. So it became like a big thing with a lot of users all around the place.
It actually give the students even were able to actually save pregnant ladies who were about to deliver. They brought in the soldiers to rescue through helicopters at the right time. They were airlifted, and the moment they landed in the army hospital, they delivered. They even they helped another set of ladies to do tele-delivery on top of a building because there was no way to escape them within that time. So the people joined together on a telecall. That basically the doctors instructed how to deliver, and then the delivery happened on top of the building. So it had so much dimensions of bringing in different types of technologies together with the social element, and then actually saving the life. And there was no hindrance by thinking that I belong to this area or that area. Everybody worked together, and all this helped us to actually build the adaptive and integrated community disaster resilience, bringing in preparedness, response, and mitigation. Preparedness through the crowdsourced mobile applications ahead of time itself, social media based awareness programs, and IoT system for monitoring. Response, as I said, through the Amrita Kripa mobile application, 24/7 call center, in-field monitoring and mitigation, IoT system for early warning, risk communication using mobile application, early warning using social media. Now, not only that, we have come up with another application called a Landslide Tracker. This is built as part of our project called Landslide, which is funded by NERC UK, where we are working with BGS, UK Met Office, King's College London, Geological Survey of India, and National Research Council of Italy. So we built this mobile application, which is also freely available in the Android Google Play Store, and people are basically using this crowdsourced application to track the landslide, because most of the time what happens, administration, by the time they come to know where the landslide happened, by the time they go there, they will lose all the details of those landslides, because we need to know the landslide event details also, to not only to save the people, also to develop all these thresholds. So we are actually trying to make sure that by bringing in these solutions, it can help both the thing, and all these things will provide an adaptive integrated community disaster resilience. So solutions adaptable to dynamic risk variation, integration of technical, social, and managerial solution. Now we are actually working with Indian Meteorological Division to come up with impact-based forecasting for landslides, because Indian Meteorological Division gives rainfall-based forecasting. So they had seen our work and they had now joined hands with us, and also the RGAS company, the ISRI India, are also joining, so that geographically based, impact-based warning for landslides and floods, we will work together, and together we are going to implement that. All these we are able to do is because of the integration of multiple multidisciplinary research areas. So what is the most important learning we had is we cannot stand as silos. We cannot stand as islands. We have to work together with our domain knowledge, with our sensor systems coming in, signal processing coming in, data coming in, modeling coming in together, so that we can give an effective warning. Otherwise, we will not be able to save the life. We will always sit as silos. So we have to, this is the time where we all have to work together with a different expertise to give the proper solution for the world, so that we can have some societal benefit delivered through our research work also. Next slide, please. So all this will
Maneesha,
help us.
Can I ask you to come to the conclusion in
yes, it's
2-3 minutes?
There.
Yeah.
Yes.
Sorry. Thank you.
So all these things. So if you see that we are able to provide an effective geospatial monitoring by integrating Internet of Things, remote sensing, machine learning, earth system science, big data analytics, modeling, geotechnical monitoring, GIS, etc. Can you go to the next slide? So all these things together, we are able to build a comprehensive early warning system, which is able to capture site characteristics, landslide laboratories, modeling and simulation, sensor systems, all the required algorithms, the communication system, software system, dynamic learning system, and multi-level warning. So it has so many pieces which has been knitted together to provide this solution. Could you go to the next slide, please? So based on this, lot of technological and scientific advances. The most important is we were able to bring in a low cost and low power IoT based wireless sensor network system for landsliding, integrated with machine learning based multi-parameter prediction and decision algorithms, and context aware techniques for sustaining the IoT systems and real-time decision support. And the major thing is we are also integrating it with a modular and scalable lightweight middleware framework for landslide monitoring and multi-site real-time management itself. Could you go to the next slide, please?
Yeah, needless to say, I mean, this is 15 years of work. So, so there's a lot in there. Yeah.
And this has led us to have the World Center of Excellence on Landslide Disaster Reduction for the International Program on Landslide. We got it for the year 2017 to 20, which got renewed now also to 2021 to 24 also. These are the different laboratories we have at the university. And can you move to the next slide? And which has brought in more than 10 international projects from the European Commission, from the Indo-UK, Indo-Brazil, Indo-Italian, Indo-Japanese, Indo-German, with 25 key research partners and four joint research centers, one with British Geological Society, one with Politecnico di Milano, Italian National Research Council, and Roma 3. Could you go to the next slide? And naturally, with all this societal thing, we are not throwing away the our quality publication aspect also. We give more importance to there also, which has helped us to bring in high impact publications. Could you go to the next slide? Next slide, please. And the key performance indicators, if you look, we have more than 20 projects in this short span of time. We have 20 US patents and 20 plus partners, leading to 6 products with more than 900,000 people impacted. And not only that, in 2019, the current Prime Minister has announced to the whole world in the Indian Science Congress, our project is one of the innovative projects in the country and has been selected for that also. And we have, as I earlier said, it has conferred with the Center of Excellence for Landslide Disaster Reduction. I think this covers most of the points, and it clearly tells you why we are different is because we believe in the philosophy of compassion-driven research laid by our Chancellor, Sri Mata Amridandamayi Devi. She is well known as Amma. That's how that principle, the compassion-driven research, that made a fundamental change in the research perspective in this university. And as per Amma, compassion is the most important factor in life. Compassion is the first step to be taken. And if we take the step courageously without fear, then everything else will follow spontaneously. Next slide, please. And Amma has reiterated this several times. And in her talk in the UN on July 8, 2008, she has said that we should take into consideration how much we have been able to use research to serve the lowest and most vulnerable strata of society. That is what we are doing. And we look forward with our collaborators, and we are very happy to work with your team also. Thank you, everybody. Sorry.
Thank you very much, all of you. Thanks for your patience sitting through the whole thing.
Thank you very much, Maneesha, Balaji. It was first a pleasure to see you again. We spent some time in your nice country a few years ago and really touched with our hands the big problem you have there. And it was really interesting to go more deeply in the knowledge of your system, how does it work, and to see how many lives you could save with your system. Probably there are some questions from the people here in the conference, in the meeting. One question from my side is how is the reaction of the population when they know that they have to move away from their home in case of emergency?
So in the case of the deployment areas where Amrita has deployed this solution, what we have majorly seen is like before our system was there, before our system was there, people used to evacuate themselves during the monsoon season because they had the fear of the landslides and they used to run away from that place. But now they wait for our message, and then only if we give warning they change. And whenever we say that we have to evacuate, they know that only when it is necessary we are safe. So they take it seriously, and we have had several community engagements, and that community engagements has helped them to build the confidence and how they have to prepare when they have to go for the evacuation.
Mm-hmm.
Yeah, actually, I would also like to add that part of our deployment scenario is we do several engagements with the community. Usually there is a local head, there's a local, group of people who make decisions for the community. So we actively engage with them right from the beginning, even as we are doing the deployment. So it is actually for their benefit that we are doing everything. So we make that point very, very clear to them that, we are not doing anything for our sake, we are doing it for their sake. So that kind of, build up that we do right from the beginning really helps us. In both our locations where we have deployed, we have a very healthy partnership with the communities.
One more question is about the price of a single probe. Is an affordable price for a small community? Or does the government or some institution support the buying of that probe?
The current deployment is based on the research projects funded by different agencies. So what we are doing is the first deployment is where we have learned. So we have put a lot of sensors to learn a lot how it changes, how the behaviors are. And in the process, what we are trying to do is we are trying to develop models which will help us to optimize the number of sensors needed so that the cost can be reduced. So we work with the National Disaster Management in that. I don't think in India they are seeing this as a commodity to sell. They see it as more of a government level work of taking this to the field.
Yeah, and also that the communities where we tend to deploy this are really low-income communities. So I don't think they will even think of adopting a system like this locally. So it has to be sponsored by the government for the most part, yes.
And it is more or less for a very high landslide prone areas, I would say. It's not for like very infrequent landslide areas. These are historically hazard prone and they know that it is, and then you have populace there. So that's why you need these type of systems there.
Yeah, thank you, Maneesha and Balaji. If there is any other question.
If I may ask something, I was thinking about the maintenance of so many sensors, so spread in the region and in the case studies you deal with. So I was wondering how about the maintenance of so many sensors? Who is in charge to deal with? Is the local government? Is the, I don't know, maybe a committee from the local inhabitants? So if you can say something about it.
So the way we have worked out is we worked with the local community. They have identified a person to look after this particular system itself. And we also have a group of community members who are living around it. They take turns to see what it is, how it is, because they are engaged from the day one when we were developing the system itself. So they were part of the co-design process. So they think it is their system. So we have built in that buy-in from the people from the day one itself. And the second thing is not only that, when we have developed our hardware and the software system, as you had seen the different layers which we explained, we have brought in the fault tolerance into it and maintenance layers into it. It is inbuilt into it. So whenever a sensor goes faulty, it triggers a message or an event to the research team to know that this is what is happening. And whenever there is wireless connectivity goes, it has a protocol which will take the next connectivity and still send the data, but it will inform you that the other one has gone wrong. So we had put in those redundancy as much as needed, and also the protocols which will move around. Plus we have local person, one person for each field, who is specifically looking into that everything is fine every day. You may have some field parameters to take it. If there is any field changes, you may want to know how the power cables, if suddenly it doesn't work, etc., etc. Things like that, you have one person which is deputed by the community itself. So there is a committee who looks into it.
Yeah, and we are also moving towards a model where we can be more flexible. So if somebody wants to do the maintenance, wants us to do like a turnkey approach and then take over the system. Right now, we don't have that scenario, but we are working towards something like that. In fact, we have something going on with the Kerala government here, where we are trying to work something like that out, where we'll develop a system, deploy it, and then they take it over at that point. So I think that is also open, right, Maneesha?
Thank you.
Yes, sir.
Another question, Marco, we would like to put to our guests about the sustainability in terms of capacity development of human resources. What are you doing to support the capacity building and development of local communities?
So in the capacity development, there are few different modules which we are looking into it. One is majorly with respect to, we initially have work which we try to see what is the community readiness level, which will tell us like how much knowledge they have about this problem itself. And based on that, we design our capacity development programs. And in that, the first and the foremost is making them understand about landslide phenomena and its variabilities, and what are the different precursors you may see. If you see such a precursor, how do you inform the people, etc. The second thing is a group, as I said, that a group of people, we basically build them as a field technicians who is able to maintain this system, who is able to actually communicate to the local people, saying that, okay, this means this is what it is, because they always think that I have to get a red alarm. That is what is warning. So that was the first level of their thought process. But as per the disaster management policy, we cannot put that in India. So we have to use different models. So, but we have to make them understand what they think as red, how does it translate into in our system, and how is it happening. So we had to do a lot of mind mapping methods. We had to do so many participatory approaches to make them understand what they want and how it can be, and then we take forward into that. The third thing is we also have done is, if such a scenario, a multi-hazard comes, how do they have to get ready? So they're packing the bag, what are the things to be needed, what is the minimum they have to need, where is their rescue location they have to go, what is the route they have to take. So that also we do with them. So those are the different things which we have done. And we had planned, and with respect to the landslide tracker app, so we are now, what is happening is these communities, we are basically making them use the landslide tracker app. In that process also they learn. When I take a video about a landslide event or a photo about or when I inform those things, they are slowly understanding what are the different types of landslides, what are the different. So we give a few people as a trusted individuals who get trained into that aspect. These are some of the initiatives which we have taken. I may have missed out something. If Balaji remembers something, you can add it.
Yeah, I think the point is by far the biggest factor to the success of a program like this is the community buy-in. So unless we work something like that out, you can develop the best technologically advanced system in the world. But if the community buy-in is not there and they are not believing in your system, then it's simply not going to work. So, and that was one of the reasons also, like I was mentioning from the beginning, from the very day one of our deployment, we get them engaged. And like Maneesha mentioned, we also, especially in Himalayas, what we did is we brought in some of the local people as decision makers, as co-decision makers. So they also feel it's their system also. So that kind of buy-in has to be there. Otherwise, it's just not going to work.
Thank you again, Balaji and Maneesha. Is there any other question? So I really want to thank you again, Maneesha and Balaji, for your speech today and for the collaboration we started a few years ago. And yeah, we hope to continue with this collaboration. And as you know, we always are interested in strength this collaboration in both with the student involvement or in other ways, academic activities. So I hope that we will continue in this way.
I may add a short comment.
Okay. Yeah, thank you.
Yeah, sorry, I had to break for a few minutes. So I also want to thank you, Balaji and Maneesha, very much for your presentation. I think it's an impressive work, long-term work that you did in this last 15 or so years, and I think it's a nice. It's a very nice example of how a university can develop and apply new knowledge and research for the benefit of communities, in this case, to properly protect and prepare them to cope with this type of risks. So yeah, I really like the interdisciplinary approach and the integration between the technical and the social dimension. So thanks also from my side, and also for accepting our invitation to this seminar today.
Thank you very much, Guido and Marco and everybody who has joined. It's really a pleasure and honor for us to work with your team, and we enjoy and we look forward to work further with you.
Yeah, thank you for the opportunity, and we hope we'll have more such instances in the future where we can work together closely.
Same for us. Thank you very much.
Thank you.
Thank you.
Sorry, before saying goodbye, maybe Nicola can share the results from the instant poll that we have done at the beginning of the webinar.
One little stuff we missed. Yes, I will. I don't
Thanks.
have the permission.
And we also have to speak, but only with the students about the final test, correct?
Yes, it is.
Yeah, okay.
Massimo, you should give to Nicola the permission.
Yeah, well done.
Okay, great.
Well done.
Okay, thank you. I will go really quick. Let's have a quick look to the question about landslides and really general. The first one is, one second. Which of the following is not a landslide event? This was generic list, and the question the most answered is floods. Sorry. Yeah. The second question was talking about triggering factor that, as mentioned by our guests, may be from natural and human-made intervention. And the correct answer among the present are actually droughts, and the other may be triggering factors for landslides, according to the article below. And to this question, the early warning systems, you answered really well, because as mentioned, the term early warning systems is defined as the set of capacities that are necessary to generate and disseminate timely and meaningful warning information to enable individuals, communities, and organizations that are threatened by a hazard to prepare and act appropriately and within sufficient time to reduce the possibility of harm or loss, as our guest perfectly described. And so thank you very much. This was just a brief sharing of the results.
Final picture, as usual.
Yeah.
Please switch on video camera.
But please don't go away after the picture. We have two things to discuss with the participants.
Ready? Everybody.
Smile, smile. 1 second, sorry. I will take one more.
Okay. Almost everybody.
Okay. So we have two issues to discuss with the participants. If they were not discussed in the short period when I was leaving. So first, we would like to know, as organizing team, your opinion about this webinar series and your suggestions, your feedback. This will be extended to all participants, not only to the people who are present today, of course, but we wanted to warn you that...
is that okay if I leave?
Oh, yes, sure, Maneesha. Yes.
Thank you.
And
Thank
Balaji.
you.
Yeah, we have technical information now. Thank you very much again.
Yeah, thank you. Thank you so much.
Thank you.
Thank you. Bye-bye.
Bye.
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 So as I said, we would like to know, to learn from all the participants how this series was. And so we prepared an assessment, basically form, and we kindly ask you to take some few minutes to fill it. so that we can have an overall impression about the perception that you had and that all participants had on this series. It was the first time we have organized it, and we are hoping to give continuity to these initiatives, but we need to probably to adapt something, to correct something, to improve something for sure. So please take some time once you receive in a very short, in the next days, you will receive this form to be filled, and take just these few minutes to fill it. It's very important for us to fine tune the organization and all the aspects of this initiative. And of course, if anyone who is now present wants to give just a quick impression now, he or she is more than welcome.
Why not?
But if not, we are sure, we are confident that we understand the time is a bit close to dinner time. So then there is a second thing, is for the students from I think mainly from environmental engineering, but anyway from the Trento students who are looking for the credit from this seminar series. We have a final test. The final test, so I don't remember now to which extent we describe the final test. There will be, again, within this week, a communication to all of you about the requirements of the final test. And it will not require a huge amount of work from your side. One credit is a total of 25 hours of work, of learning work. So it will be enough that you have participated to the seminars. Maybe you look back to some of them or to some parts of them, and you integrate with some reflections on your side about the main topics of the webinar series related to environmental sustainability and international cooperation. Basically, we are interested to get some reflection from your side and some rethinking from your side of some of the inputs that were circulating in this series. But we will send around an email to all students, registered students who are looking for also the formal credit recognition, explaining in detail what the assignment is.
Deadline.
Yes. I'm from here. I cannot access the chat. I don't know exactly where it is.
No, I was writing the details from the page of the website, and I think that the most remarkable thing is that deadline for submitting the paper was extended to the mid of July, so you have more time to submit.
But as you can see from the reminder that Livia put on the chat, we are asking for a short document, not too short, minimum 1 page, but maximum 2. So it's really aimed at getting the personal reflections you have after this series. So third, I really want to give a huge thank to all the ESIC team, because I was the one who did the list, the minimum effort, but all the other ones put a huge effort in all the backstage or the organization, all the communication or the graphics and recording. And I mean, there is quite some management behind the whole series. So really thanks a lot. It was thanks to their, I mean, to the enthusiasm, the energy of all of you that this webinar has been possible. And so, yeah, that's a big thank from my side, and I think from our side.
Thank you. It was a pleasure to be part of the team, of course.
Thanks a lot for participants resisting for 8 times.
Yeah.
Great participation. Almost 120 people enrolled. So it's a successful first edition, in my opinion.
I agree.